we discuss something related to molecular docking analysis, isn't it? Whatever we talked in Autodoc, I tried to explore how to analyze the results using Discovery Studio Visualizer. I used BioVia Discovery Studio Visualizer, and I have also used MATLAB Symbiology tool. Okay, how do you analyze pharmacokinetic models? Okay, and also how to understand pharmacodynamics using MATLAB Symbiology tool. What I have done, I have taken an example. Okay, I've taken a model, a cancer, working on a cancer model. I try to check the effect of two different drugs onto different dosages. Okay, using the MATLAB Symbiology. Okay, so I think that is just an exploration of how to work on analysis using Discovery Studio and how to work on PK or pharmacodynamics model on MATLAB Symbiology. So I think there is no need to ask any questions on that. So let me go to whatever is left out. I have mentioned you about virtual screening, and I differentiated what is the difference between the general molecular talking and virtual screening. You remember molecular talking, okay, if you see even in Discovery Studio, if you see a package like Discovery Studio, we have one kind of tool called TS ligand fit. This talk, okay, only one ligand with one receptor. Okay, so the docking of one ligand with one receptor is possible with TS ligand fit. There is also one more module called libdoc, LIBDOCK. This is used for docking multiple ligands. Okay, multiple ligands with only one receptor at a time. This is what we call it as visual screening. You know, in Discovery Studio itself, we have two different modules. One for using the normal ligand receptor docking, the other for virtual screening. We also have one more module called ligand score. So the Discovery Studio ligand score is going to score as you will be getting 8 different scores. Okay, instead of getting a simple energy score, you will be getting 8 different scores from Discovery Studio ligand score module. Okay, whereas if you take Autodoc, okay, whatever Autodoc Mina, Autodoc 4.0, Covalent Autodoc, this is used for docking one ligand with one receptor. But if you want to dock, okay, multiple ligands with a receptor, go for Autodoc PYRX. Of course, this also multiple ligands with a receptor. Of course, is a product of an Autodoc. Okay, whatever is shown as a PYRX is also a product of Autodoc. Okay, so I also mentioned what tools you have to use and what kind of scores. And here, can be an Autodoc or Pyrex, you get only one score, that is internal binding energy score. You won't get the other 7 scores, whatever you get from Discovery. So likewise, you can compare and study. It will be easier for you. So let me take you to the Autodoc PYRX. Okay. If you want to install Autodoc PYRX, simply in Google search PYRX. Okay, or Autodoc PYRX download. Okay, so defaultly it has to take you to the pyrx.sourceforge.io. This is the home page for it. Okay, you have to install only one software. Unlike the Autodoc, I told you to download and install 4 different softwares, isn't it? LGL tool, Chimera, another whatever I mentioned. Okay, but here you have to install only one tool. Okay, only one software you have to download and install. So it is easier for you. There won't be any problem for you while downloading an installation. So now I have already installed the PYRX. Okay, in my system. So I'm just simply opening it. So I'm directly going to explain you how to use the PYRX tool. So before that, I suggest you to have a separate folder for a ligand and a receptor files alone. So for Autodoc, I told you to keep a folder to store Autodoc 4, AutoGrid 4, and a tutorial if possible. And you must store even the receptor and ligand files, isn't it? You are going to download and save these files in the same folder. But here in Pyrex, you can have only two files. One is the 3D structure of a ligand, other is the 3D structure of the receptor. Now I am going to save a folder called pyrx demo 4. Okay, pyrx underscore demo 4 in the desktop. Okay, so I better take one kind of a receptor. So now I'm going to try with a receptor called insulin growth factor receptor 2. Insulin growth factor receptor 2. Actually, this is a kind of a modeled receptor, but if you want to try with a kind of protease, okay, what I tried on yesterday for molecular docking, I mean, day before yesterday on molecular docking, you can also try this, okay. So whatever protease, I think the PDB is not one, even this is actually modeled one, but the demo file, what I'm going to show, I just show in the Windows slide. The PDB ID for this is 5L3L. Okay, 5L3L. So I just paste it. Okay, because even some participants are asking for exact examples. They want to practice it. Okay, so Python RX programming. PYRX, no? Python RX. Basically, use Python programming to go for virtual screening. Okay, this is the PDB ID I used for receptor. Okay, now I take you to the ligand file. So if you want to download a ligand file, you should not download a single, but you have to download a combination of ligands in the form of a data set. For downloading the ligands, I suggest you to go to the NCBI PubChem. So in PubChem, you can type some series of compounds. Okay, myself in my PhD research, I worked on voirovinones. Voirovinones or a group of rutinoids present in a plant called Voirevia diffusa. Okay, so this is actually I told you used for treating the kidney stones, to remove the kidney stones or to treat the urinary infection. We better go for this, but also it is used for treating other cancers. I have reported that it's also used for treatment of hepatocellular carcinoma. Okay, so I'm just taking this Voirevinone. There are a series of compounds, nearly 14 results we got. For example, Pyrimidine B, you have a PubChem ID for that, and Pyrimidine A, the corresponding PubChem ID is shown. So you have something like that. Okay, obviously you have some 14 compounds of that. But if I want to take all these 14 compounds for illustration, it takes more time to demonstrate, isn't it? So I want to make some filters. I want to reduce some compounds. So what I'm going to do is to reduce it, I choose my desired filter. So for this, you have to click this filters. I'm just clicking this filter. Okay. Now you can see all the physicochemical properties of that 14 drugs. Okay. All the 14 drugs are lying in this bar diagram. Now I just want to touch only the two properties to reduce the 14 count to less than 5 or 6. Okay. So less than 6. So for this, I'm going to try with the molecular weight. Okay. So I'm going to choose, okay, molecular weight 320 to 350. Okay, this is what now I presently focus. And I'm going to use the hydrogen bond donor, okay, as 2 to 4. Still, I got 10 results. Okay, but if I want to go for the next anything acceptor, okay, the acceptor I'm going to try with the 7. 1 day 7. So, three properties I have touched now. So, even I got 9 results. Okay, no problem. So, uh, for a for a filter, okay, I've used a filter, okay, and I just reduced 9 out of 14 in my compound selection. So simply what you have to do after selecting all this, click X mark. Now you got 9 results here. So simply you have to download all these chemical molecules in the form of a data set. For this, you have to click download. If you click download, you get a coordinate as 2D and 3D. You have to only try with the 3D. Okay. And now whatever you download, it should be in SDF form, structure data form, because this is actually used by Discovery Studio. Okay. Go to the desktop. Now I'm going to save this as Poirevino. Okay. This is my plant compounds. Okay. 9 compounds are saved in .stf format. Of course, this can be visualized using Biovian Discovery Studio. Okay. Now just like I saved. So whatever I said, if you want to check whether all the 9 compounds present or not, simply right click here, open with Discovery Studio 2023. So we have to check that also. Okay, so not just downloading, you have to check how many structures are downloaded. I can able to find only the 8 structures. I think one structure you don't have a proper 3D. If you don't have a 3D structure and only the 2D structure is deposited, now we can able to find, isn't it? Out of 9, only 8 structures are available. If you want to see all the 8 structures, okay, simply select all the 8 structures and show in graphics view. See, all the 8 structures are available in the form of a single data set. So 8 different covalent compounds. Now I have to try to talk with a receptor called insulin growth factor receptor. Like if you are trying with a cancer and a kind of a diabetes, okay, if you want to work, okay, the effect of the kind of these pheromones on both these diseases, okay, you can study also a period review of diseases with a single drug, okay, or a combination of drugs. You can check which is the best drug from them. So this is an example for that. So this is an insulin growth factor receptor, very small protein, isn't it? So why I've chosen this protein is I want to choose only a small protein so that I can complete as soon as possible for demonstration. Okay, you can try with any receptors. Okay, now I just going to try the virtual screening using Autodoc Parex. So I've already opened the Autodoc Parex. The Autodoc Parex tool window looks like this. Okay, I suggest you to go for use the first step like set the path. Okay, so initially you have to set the path for the output files and the intermediate files generated from the Autodoc PYRX. So for this, go for edit preferences. In edit preferences, you remember the name of the folder? Yeah, I think PYRX demo 4, isn't it? So this is the latest folder. So PYRX demo 4. This is my directory name. This you have to save it in workspace. In C workspace, okay, wherever you have located the ligand and receptor files, that location should be typed. Okay, so I just typed now. I clicked OK. So now I will save the path in edit preferences. Now let me go to the first step. The first step after the setting the path is file load molecule. So load molecule here I mean the macro molecule. Okay, now I'm going to click file load molecule, but it's showing somewhere else. So better put the desktop. Okay, unlike Autodoc, here you create a kind of different location to open any files, but you go to the desired selection. Okay, it's there in the desktop, isn't it? So that is the PYRX demo, and this is my protein receptor. Simply click open. If you open this protein, okay, sometimes you may also get just because it's a model structure, you got nearly 20 different models. I can't able to take all the 20 models for docking because it takes more time. I want to choose only one model. I consider the first model is the best one, so I try to delete all these remaining 19 models. I keep only one model selected for docking. Okay, so you got only one model. So initially I got 20 models. I just want to check with model one, so I deleted the remaining 19 models. So this is the first step I made with the protein. And then next, select this. Now right click, you get Autodoc. Okay, if you see here, Autodoc make macromolecule. Okay, Autodoc make macromolecule. Okay, now simply watch this. Okay, so what I'm going to do. So just I'm clicking make macromolecule. The process is completed. Okay, so first what I did, edit preferences. I didn't prepare a protocol, so I'm sure giving you a demo one more time. First edit preferences, set a path. Okay, and now I'm going to click file load molecule. Just uploaded a kind of a protein molecule. Now I clicked right click here and Autodoc, and now I click make macromolecule. Okay, 3 steps are completed, including the path setting. Now go to the fourth step. Okay, 3 steps are prepared. I mean, even the protein file is prepared. Okay, if you see the protein file here, initially we don't find it in PDBQT, but after making this third step, you got like a protein.pdbqt. Initially it is in PDB. Now you have converted this file as PDBQT. I already told you in Autodoc, it can be Autodoc Winner, Autodoc 4.0, or Autodoc PYRX. You have to convert the input files, that is both ligand and receptor, in the form of PDBQT. Okay, so the receptor is prepared now. Only thing is that you have to prepare the ligand. You have to load the ligand and you have to convert it as PDBQT. That is the next step you have to make it out. Okay, so to make these ligand molecules to PDBQT, remember initially how we have downloaded the ligand molecules from the PubChem. We have downloaded this in the form of a data set in the form of .stf. It's not in PDB. It's not even in PDB or PDBQT. But whatever format you have to convert as PDBQT for working with Autodoc. So the next step, what I'm going to do here is open Babel. I click open Babel. This step is used if you don't have the ligands in PDBQT format. Okay, so I click the open Babel. This is the fourth step. Here you have a plus sign. It asks you to insert a new item. Simply click here. Okay, it's not directing to the exact folder. So I'm just taking to my path, PYRX demo. So what I have to open? I have to open the ligand. Okay, so this is the fourth step. I'm going to make it out. So now we got nearly 8 ligands are open because only 8 structures are known for the 3D. Okay, you don't have that ninth structure, isn't it? So simply I'm just reminding you. So now I select all these 8 ligands. Okay, now I'm going to right click. After selecting this, I think no need to select all this. Simply click the first one. Okay, right click. Simply select the first ligand. Right click. You get like if you go for energy minimization for the selected ligands, you can do docking with only one ligand, but you want to do docking with all the 8 ligands, isn't it? So do the energy minimization protocol by clicking minimize all for all the 8 ligands. Okay, this is a simple step, selecting one ligand and clicking minimize all. Now energy minimization has happened. Okay, so for all the ligands, energy minimization is completed. So even the energy is mentioned here. Here earlier we don't have, now the energy is projected here. Now right click here, convert all to Autodoc ligand PDBQT. So even clicking a single ligand, you can able to convert all the ligands in the form of PDBQT format. So for this, that is each and every ligand is going to have a PDBQT format. Okay, for this you have to select this option. Now convert all to. So now if you see, all the ligands are converted as PDBQT format. Okay, so to know more about this, okay, even I think you can find somewhere. Yes, you have converted all these molecules. Yeah, now you can see here in the ligands. Each and every ligand. Okay, initially we don't have. Now only all the ligands are converted as PDBQT. All the 8 ligands are converted. So you have completed up to the fifth step. Okay. Now the sixth step is to go to Vina Visa. The sixth step here is you have to direct to the Vina Wizard. Here it is asking to start the process. You simply have to click start. Now, if you see here, this protein molecule is selected now, but the ligand molecules is not selected. Here you get like a message like no ligand getting selected. So you have to select all the ligands for talking, isn't it? So if you select one ligand, you get like one ligand selected, but you want to do a talking with all the 8 ligands. So shift select, then all this 8 ligands are selected. Whatever 8 ligands you have selected, here you can able to find here. 8 ligands selected and also the protein molecule selected. Ensure the ligand molecules and protein molecules are selected before going for visual screening. Okay. Now, this process is completed. Simply you have to click forward. If you click forward, okay, you can able to find a protein and a grid box. You remember such a kind of auto grid we observed in Autodoc. Here also you find similar kind of an auto grid. Our objective of using the grid is to enclose the protein in the grid so that you won't miss any binding sites. Okay, so this is our objective. Simply select this grid, but it's in the 2D, isn't it? To get in the form of a 3D, there is a cubical box here. Okay, to obtain an isometric view, simply click this. Now we can find this in 3D. Okay, so you have these atom selections. If you want to increase the size, simply drag. Okay, so very simpler for you when compared to the Autodoc. So to map the boundaries of the protein, I think I have mapped, but still I want to reduce the time, and if I want to perfectly map my protein, I simply click maximize. If I click maximize, earlier whatever I prepared is a large grid, but now whatever grid, it's automatically the system has detected and optimized is a smaller grid. So during the virtual screening, it takes less time. If I go for my manual kind of thing, it takes more time. but I maximized, I mean, like this is the best fit of your receptor on this screen. So simply click this maximize. We got this boundaries. Now simply you have to click forward. If you click forward, that's it. I have completed the process. The entire process is complete. Now all the 8 ligands, okay, are going to go for virtual screening. Okay, you're going to talk all these 8 ligands. First 2 ligands are already talking. We're waiting for the other. So 3 ligands stopped. See how much fast you're completing this process. Okay, actually mine is a kind of good configuration. So I found nearly 20 CPUs. Actually, I think 20. I have 20 threads. It seems it's an i7. It's a good configuration system. So I can able to complete even the virtual screening as soon as possible. If you have i3, if I can able to complete here for 2 or 3 minutes in i3, you may take even 7 to 8 minutes. i5 nearly 4 minutes. So the time is different on your processor as well as the RAM capacity. Now, all the 8 ligands are docked. Each and every ligand is going to generate 10 poses, 10 different poses. The first pose, what we'll be getting? Okay, so if you see here, I got like minus 7.2, okay, for a ligand. So you can able to see a pubchem ID 12004175. So you can able to find 10 poses for a ligand. So totally you have 8 ligands. So 10 into 8, how many results? It has generated 80 results. If I drag and show, you might have got 80 different. But I think not 10 poses. You got nearly 9 poses. 0 to 8 AdSense. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. So, okay, not the 10 poses. I got 9 poses. So, totally 9 into 8. So, we got 72 different items. Okay. If you want to download, even you can able to download the result. So, in the analyzed result, we have something called set preferences. But we can save as comma separated files. Save as comma separated files. This can be stored in Excel sheet. Okay. If you want to save this output in Excel sheet, you can able to save it, all the 72 results. So now whatever I have, okay, so I'm going to save it like output. Okay, default if you save it as output.csv is the file name. Now I'm going to open this. Okay, you have an output.csv, so I better zoom in and show it in the Excel itself. Yeah, so this is the results we got. Okay, so if you see here, for a ligand, okay, you got this kind of a result. So I think better I can go. This is the RMSTs, but the major thing you have to concern is the binding affinity. You should have negative maximum energy. Actually, whatever binding affinity here they have shown, okay, is in kilocalorie per mole. The unit of this is kilocalorie per mole. So if you want to find which is the best ligand, I suggest you to go for using the filter. Click the data, go for filter. Okay, you can check which is the highest score. The highest score is the minus 7.2. So deselect everything, just select minus 7.2 and see here. So you have nearly 4 different ligands. Out of 8 compounds, 4 compounds have shown the negative maximum energy. So not you didn't get a single result, you got 4 different ligands. So what I suggest is after going for visual screening, go for manual docking using AutoDock. Then only you can screen in the next step. If you want to find which is the best one, okay, you have to go for manual docking with each and every ligand or with all the 4. You can neglect the other 4 ligands. Okay, if you want to find what exactly, okay, what is the name of the ligands, okay, so you simply have to copy the pubchem ID, okay, and go to the NCBI pubchem, simply type that, you will be getting the exact, the first ligand what I've shown is the querinone. And similarly, you can check for the second, third, and fourth, and you can check what are the base ligands bound with the insulin growth factor protein. Got it? So that's it. I have completed my part in virtual screening today. Now, if you have any doubts, you can ask. I have completed my demo. Could we do multiple chain protein docking. Yes, we can make it out, but takes a lot of time. Any other doubts? Yes or no? Can I move to the next simulation? MD simulation?
I have doubt, but I didn't type in. I just can I ask it orally?
Yeah,
Uh,
can
my
ask me.
uh, my doubt is, sir, as you also saying that no other software required for pirates. What if we didn't have Autodoc in our system and only a pirates? Then it works because as it's showing that it does working with virtual screening with the help of Autodoc. So is it works when we only have pirates, as you
Yeah, yeah,
mentioned?
yeah, yeah. It works. Actually, even the Pyrex is going to use not only the Python programming. Obviously, it uses a Python molecular viewer for viewing the molecules. So, of course, it is integrated. So, the Python molecular viewer is integrated with the PYRX. So, obviously, one can able to work okay without Autodoc software. So, Autodoc PYRX is the exclusive one. If you find any problems with it, I think you can also install the Python molecular viewer, which is associated with it. Any other doubts? I think no. So let me
Another,
go to the
another thing,
yeah.
sir, can you share the manual or something that
Everything is available here, madam. Is available in the website Python prescription virtual screening. Of course, it's recorded, isn't it? So I remember that for this demo I showed very relaxedly. So I think you just pause and play. Okay, so multiple times, then only you can learn. So each and every step has to be practiced perfectly. Okay, don't change the step. So I think it's available in video tutorial now. Now let me go to the MD simulation because if I go to this again once again, then you will be missing some concepts in MD simulation. So and I think a participant has
no issues. Thank you, sir.
good. Thank you. Thank you. I think I have cleared your doubts. Only thing is that you have to practice and get a conference on it. How to do multiple chain docking? Yes, simply same protocol. Nothing. Like however, I just opened the virtual screening. Okay. So how I just opened and I just have done. Okay. Simply if you open a protein molecule, even multiple chains, whatever you get, obviously your ligand is going to tie with all the chains and you whatever results you get. But you know, the one disadvantage is that you can't able to find the hydrogen bond interactions. You remember on yesterday, I was explaining you like the hydrogen bond interactions. Not only you got the hydrogen bond interactions, you got pi-pi bond interactions and other kind of interactions also, isn't it? So all the interactions are visible in the 2D interactions. So you can able to go get the hydrogen bond interactions. You can get the 2D and 3D structures. But here you won't get anything. You get only the energy alone. So this is a prior tool before going to the molecular docking using Autodoc. Before going to Autodoc, one must try with the PyRX, try with the multiple ligands, screen it, and then you have to go with the any Autodoc tools. Okay. So this is the general protocol we follow. Okay. Now let me go to the MD simulation. Nothing different. Okay. The same steps. I have plenty of slides. I think here also I have 32 different slides. So let me go ahead on MD simulation. So this is the next topic. Okay, I believe I already mentioned you the difference between the talking and simulation. Actually, whatever simulation we call that is what MD. Okay, MD simulation. The simulation is nothing but whatever a ligand is docked with a receptor. If you check with respect to time, okay, that's what we call it as a molecular dynamic simulation. And if you see this computer simulation methods for this is generally used for analyzing the physical movements of the atoms and molecules. Okay, and if you see this, okay, here basically one should have a knowledge on three important subject. Okay, one is classical dynamics, statistical dynamics, and one should have a knowledge on quantum. Actually, like in mechanics, okay, in mechanics subject you have two types of subjects. One is statics, okay, the other is dynamics. So mechanics are of two classifications, statics and dynamics. And if you go for the mechanics, you have obviously classical. So what do you mean by classical mechanics? Classical mechanics is a basically Newtonian's law of motion. Okay, so you know the laws of motion, Newtonian first law, second law. Okay, so if you are studying something about the Newtonian's law of motion, then we call it as the classical mechanics. And what is statistical mechanics? if you are working on plenty of molecules and atoms, if you see a protein, okay, if you want to simulate a protein structure, generally a protein is not less than 100 mNs. And if you see such a kind of a protein, for each and every amino acid, you have a cluster of atoms. So obviously, one can able to find more than 1,000 atoms for a protein. If so, if you want to check, okay, the classical motion, okay, if you want to study the Newton's law of motion for each and every atom of a protein, then obviously one should also have to study about the statistical mechanics because you have plenty of data. Then if you see the quantum mechanics, okay, so generally if you see a protein, okay, how we can study the physical or chemical properties of a protein. So let us see in wet lab, we generally take a spec, isn't it, to measure the weight, okay, we go for the spec. So obviously what you are going to use, you are going to use the light. You're going to use the light and you find the turbulence of your protein from the spectrophotometry, isn't it? So however you are practicing this in the wet lab, the same thing is also followed in the computational lab. In computation, so they are using the light to determine even the properties of a protein. Okay, so that's what we generally call as a quantum mechanics. Of course, we use the Schrodinger wave equations to study about the to study the motion of the particles. Actually, instead of Newton's law of motion, here we additionally study the Schrodinger wave motion. So Newtonian law of motion is just F equals ma kind of a linear kind of a motion, but here you study in the form of a wave kind of a motion. So according to the quantum mechanics, they mean that each and every atom is moving in the form of a wave. Okay, even it can be a protein or any other biological macromolecule. Now, if you take this kind of a Monte Carlo versus molecular dynamics, okay, you can able to see here the amino acids of a protein, okay, on the surface are present in random. If you see a structure of a protein, how a structure of a protein depends, it depends on the folding kinetics. So if you see the structure of a protein, I think I mentioned in the first class itself, that is generally you go for X-ray crystallography, X-ray diffraction, or NMR, or even cryo-electron microscopy, whatever you do, okay, especially if you take an X-ray, you get a kind of an X-ray coordinates in the black and white spots. You also get some kind of gray spots. So whatever black, gray, and white spots you get, okay, only these spots are converted in the form of 3D coordinate file in the form of PDB. I told you how to convert this X-ray to PDB. General software what we use is the GROMAX. The GROMAX is used for actually the GROMAX is simulating our X-ray coordinate file to the PDB file. You know, even GROMAX is used for this purpose. Okay, now if you see this amino acids of a protein, okay, even the fold of a protein, okay, is dependent on the surface model. So how we can work? We can work with a kind of a Monte Carlo method to determine the exact folding structure. The proper folder gives the better stability of the protein. If and if you get a better stable protein, then only you can go for dynamic simulation. Okay, this is so and I just showed that. Right now, let me go to the types of MD simulations. The MD simulation you can carry out through conformational sampling, energetics, kinetics. Okay, we have some kind of an applications with respect to conformational sampling. What kind of applications? You can determine the even the binding pocket. You can determine the binding pockets, binding sites. You can also analyze the binding paths. Not only the binding site regions are analyzed using conformational sampling, and even the rearrangements. Okay, like for example, if you see the spike glycoprotein of SARS-CoV-2, initially for the first time you have only one kind of a protein structure. But if you go for the mutations like alpha, beta, gamma, so you have plenty of mutations, obviously, some kind of a rearrangement of binding sites are happening, isn't it? So to know about that, okay, how effectively even the drug, whatever you used earlier for the first strain can be used to target the second strain or not. So some kind of binding sites are also rearranged. So all these things can also be checked using the MD simulation. And if you see the applications of energetics, okay, simulation of unbinding and free energy calculations. So these are you can find in energetics, and kinetics you can find sampling of unbinding events. Quantum mechanics. I told you there are three types of mechanics. Of course, the latest one, which is most used, that actually the quantum mechanics obviously uses even the classical and the statistical mechanics. In addition to the classical and statistical, here you are going to use the wave particle duality. I told you, if you don't have a linear motion, but you find a wave kind of a motion, okay, which is in addition incorporated in this quantum mechanics. Of course, all these softwares are deployed, okay, or program to work on this kind of quantum mechanics principle. Okay, it can be GROMACS, the MD simulation by GROMACS or AMBER, or whatever software in AMD. All these things are going to use the quantum mechanics. If you see an atom, I mentioned you know, if you take a protein of 100 amino acids, if you have nearly 1,000 amino acids, each and every atom, okay, is going to move like this. It can either move like this or it can move with high energy. So if so, how about the wave motions? The wave motions are shown like this. Okay, like generally, if an atom is attached to a spring, okay, to a support, so the spring moves dynamically, and based on the speed, you can able to find the wave motion. So obviously, in the wave motion, you can find sine, cos, tan, all these kind of mathematical, trigonometric, whatever you studied. Okay, all these wave motions you can able to find during the quantum mechanics. And of course, this is the general concept we use even to develop the force fields. Actually, you generally try to calculate the forces of all the atoms. For example, if you have 1,000 atoms in a protein, or the force of each and every atom, okay, you sum up to get the total force. And from the force, you can calculate the energy. And from the energy, you can go for the energy minimization. You can find the stable protein by energy minimization protocol. So actually, the kind of applying force field and going for the energy minimization, all these things we can find from the MD simulation. If you see the force field, there are plenty of force fields available. Okay, now I can take you to the force fields one by one. First force fields, actually first I can show you the types of force fields. Classical, polarizable, reactive, coarse grained, machine learning, water, modified amino acids, and other. Okay, if you see the kind of amino acids and the force fields, okay, so now we can able to understand whatever I explained. Okay, this is an illustration. Now go to the classical force field. If you see the classical force field, the first one, okay, the best examples are AMBER. You know, there's an expansion for AMBER, Assisted Model Building and Energy Dependent. This is widely used for molecules like protein and DNA. But there is a second CFF, also called as consistent force field. This is used for polymers and metals. So it depends on what kind of applications you are using in classical force field. Okay, classical, of course, it uses the Newton's law of motion to calculate the total force, and obviously from that you can calculate the energy. Actually, it is the popular force field. Most of the people try to use this charm. The charm here, the expansion is chemistry at Harvard molecular mechanics, generally used for small molecules in macromole. Likewise, okay, so you have Chromax, Chromos. Okay, so plenty of softwares are there. So these softwares uses one or two kind of force fields. Okay, even you have a charm force field in Chromax. Anyway, I think we also have a Chromos. So you can choose any kind of a force. Generally, we go for charm, working on charm using the Chromax. So likewise, you can find another popular force field, that is MMFF, Merck Molecular Force. Okay, this is developed by Merck Institute. So the detailed information you can even find from textbooks or from the journal paper. Now let me take you to the polarizable force field. So even in polarizable, you can find the same example, amber. Okay, so the same software uses both the kind of principles. Not only you're going to use the Newton's law of motion, but you can also use the polarity. You know, based on the polarity, you can calculate the force fields. Actually, if you see the uh, uh, amino acids, the amino acids can be a polar amino acids or non-polar amino acids, isn't it? So based on the polarity, if you tell it as a more polar, that is a hydrophilic. You have more hydrophilic regions on this surface. So obviously, if you have more hydrophilic, even the hydrophilic ligands try to bind more with the hydrophilic sites. You got it? So the hydrophilic, if you have hydrophilic amino acids, you can find these are the binding sites for the hydrophilic ligands. Hydrophilic ligands example, what I can mention is the phenols. Phenols, polyphenols like flavonoids is going to have more OH groups. If you have more OH groups, obviously it try to target this polar amino acids. Okay, so likewise, you can have another example like amoeba. So amoeba here we mean atomic multipole optimized energetics for biomolecular application. Okay, so likewise, we have even charm, PFF, pass orient, or some of the examples for that. Reactive force. Sometimes even you can find reactions happening on. Example, enzyme substrate. If enzyme is interacting with the substrate, what you can find, an enzyme substrate intermediate complex is formed. Not only that, later you can get the product. You can get the product from that. Okay, enzyme is released separately, and product is going to release separately. So under that, you can able to find some kind of reaction has happened. So for this, you can use EVB, empirical valence bond. Okay, and reacts after is one another course. Now go for the coarse grained force fields. Okay, dissipative particle dynamics. So if you see this, it is typically used for studying the hydrodynamics of various simple and complex fluids. Likewise, you can have Martini, Sierra, and RAM. Okay, virtual atom molecular mechanics. Energy minimization protocol. I told you till now about the force fields. I told you the total force is calculated from the force field, but our objective is even to calculate the energy and to minimize energy to make a protein more stable. Yeah, participants, are you teaching other participants? Kindly mute. So participants, kindly take care. Okay. So I don't want such a kind of a disturbance in future. Let me take you to the PPT. So even myself, I'm rushing, isn't it? If you want me to slow down, you can ask me to slow down. Okay. Uh, and if such a kind of disturbance you find, okay, even I have to skip some slides and I have to explain. So take care. Okay. Now let me take you to the energy minimization protocol. So till now, whatever explained is how to calculate the total force from the force fields. And from the force field, if you want to calculate energy, what is the simple formula you can use? Everyone know energy is nothing but force into displacement, isn't it? This is the formula we studied from the childhood. Of course, we use a kind of a distance of each and every atoms, and whatever total force you calculate, you multiply it to get a energy. And whatever energy you get, you go for energy minimization for using the steepest descent and conjugate gradient. These are the two types of energy minimization methods. Also, third method is that, but these are the most widely used methods in any software, most of the softwares. Okay, some information on machine learning. Now it's not needed for you. Let us go to the molecular dynamics simulation. I told you, generally you study the atoms in the form of a microscopy. Okay, so for that, you deploy the statistical mechanics and you study that up to the macroscopic level. Okay, MD simulation, these are the softwares, Avalon, Amber, Charm, Desmond, Romax, the expansion of Romax, Groningen machine for chemical simulations. Okay, Charm, this is a simulation software. You found the expansion. Romos, Groningen molecular simulation. NAMD, nanoscale molecular dynamics. Okay, Q and Yasra or the other simulation software. For Gromax, you have to go to this web page. Okay, the Gromax is free to download, but it works only in the next operating system. Works only in the next operating system. But nowadays, I think even we are getting some kind of interfaces. Okay, even it can work in Windows also, but it takes lot of time. If I can't able to show the practical demonstration using the Chromax, okay. For working on Chromax, myself, I work in IIT Madras. So I'm working in protein bioinformatics lab in IIT Madras. Okay, from a DST grant, we have purchased a workstation. So I think around 2.5 lakhs, and many people also purchased up to 6 lakhs to 10 lakhs. And only in this workstation, it is better to work on the Chromax. If you try with the laptops, it takes more time and sometimes it may get corrupted. Okay, so I suggest to work on the desktop computers with high configuration. So for working on a single ligand and receptor complex, it may even take 7 days to 14 days. Okay, if you try with the desktop systems, like normal i7, something like that. But if you try with a high configuration like Xeon processors, it may take less time. Okay, so we are using high configuration, so I can able to complete simulation within 2 to 3 days. You won't get within a short time. Okay, so I just can provide you some details on Chromex and how to work on Chromex. Of course, one should have a kind of a Linux and knowledge on Linux commands to work on the Chromex. And even for to work with the Chromex, you should have also have some prior knowledge on Python programming and Perl programming. So during the installation of this Chromex, I found difficulties on compatibility of linking with the software. Even I think yesterday from a participant, I came to know the four softwares are not compatible with each other. So obviously I can't able to install, sir. So this is the query raised by a participant. Of course, I just provided a combination of softwares. Like one software, if you want to has to be compatible with the other software, you have to use only the appropriate versions. You can't go the latest version, or you can't go very earlier versions. Okay, so you have to go to the appropriate versions. Even in Chromex, if you want to work, this is not a single software. Okay, you have to integrate with nearly 15 tools. Okay, I'm also using 15 different tools to work on Chromex other than Chromex. Okay, so obviously these tools have to be, if you want to integrate, obviously the compatible, you should get download and install only the compatible versions. Okay, so even the Chromex is going to create numerous intermediate files. If you work on docking, molecular docking, whatever files, intermediate files you generate, it is not more than 5 MB. But if you work on MD simulation and if you work for 200 nanoseconds, they make it even up to 4 GB files. Sometimes trajectory files cross 12 GB based on the size of your protein molecule. If your protein molecule is large, you get more time. Okay. So kindly mute, madam. So or I can remove from the call. Okay. Let me take you to the MD simulation. Okay. So we can continue about the simulation. I was mentioning about the size of the output files generated from the Chromex. Okay. So now let me take you to the MD simulation protocol. So I told you we will be fixing a time like some generally if you want to publish, you have to go for minimum of 100 nanoseconds. We can go for 100 nanoseconds or we can go for 200 nanoseconds for a good kind of a results. Okay, so for molecular dynamic simulations, obviously here they are keeping a particular temperature and pressure as constant. Okay, like how you study thermodynamics. If you want to study ideal gas law, you keep a temperature pressure constant. You work on it, the standard temperature and pressure conditions, isn't it? Even in simulation, it will be like that. If you are working on liquid thing, okay, water is the medium. If you want working on gaseous molecule, air is the default medium. So this is how they use the kind of a medium and they try to develop the simulation in the software. Okay, so whatever like for example, if you take a drug, okay, if you consume a drug through the oral route, so how the drug is going to go for pharmacokinetic properties like ADME. If you want to study all this, even the same, you can also study through this simulation using the Chromex. If so, how much time a drug can able to bind with the protein, how much it is going to reside, all these things with respect to time you are going to show, isn't it? So obviously one should know about what medium you use, okay, and of course what is the temperature and pressure. So whatever temperature and pressure we're maintaining in our body, like we know our temperature is around 37, isn't it? So the same kind of a temperature is fixed even in this simulation software. And even what pressure we have inside, the same kind of a pressure is also fixed. So whatever we are going to try with our systems, okay, biological system, the same thing is implemented in the simulation software. So generally, if you see the simulation, you can find RMST, RMSF, and energy, PBSA, so some kind of a spores. Also, you can the hydrogen bond interactions. These are some of the outputs of the Chromex software. If you see the Chromex tutorials, you have plenty of examples. Okay, so generally, if you work or want to work on a ligand receptor complexes. Okay, you have a tutorial here. Okay, actually, if you go to the Promax website using this hyperlink, okay, you can find all this in the form of an hyperlinks. If you want to know more about the tutorial, stepwise tutorial to work on the protein ligand complex, you have to simply click here. If you want to, you can also work MD simulation like the effect of lysozyme in water and something like KLP15 in TPPC in high lipid membrane. How about the interactions? Okay, and how about the free energy solution, biophysics? All these things also you can study other than the ligand receptor interactions. Now, let me take you to the next page, that is Chromax tutorials. If I click the hyperlink and if you get inside, obviously you get this kind of a page, nearly 1, 2, 3, 4, 5, 6, 7. 7 steps are there. Okay, so the first step is to prepare the protein topology. Remember, I provided you the Autodoc tutorial. Similarly, even in Chromax, there is no need to provide the tutorial because this tutorial is already available in Chromax website in the URL mentioned below. Okay, so GMX stand for the Chromax. If you want to work on Chromax in Linux mode, you are going to use a command called GMX. Okay, so even there is some kind of a link based on that. If you see this kind of steps, okay, 9 steps are there. First step is to prepare the protein topology, whereas there initially in Autodoc what we made, we also prepare the protein, isn't it? The second step is to prepare the ligand. Here also the same, but here to prepare the topology. Okay, so you are doing some additional steps. So in Autodoc, if you compare Autodoc and tutorial and the simulation Promax tutorial, so Autodoc tutorial is just up to the 1 or 2 steps, only the 2 steps of the simulation. You have plenty of substeps in the 9 steps of MD simulation. That's what I want to make. Plenty of substeps are there. Okay, so nearly, so you have to work 15 to 18 commands. Okay, more than 15 commands. Comes around 20 commands to come up with the final result. Okay, so prepare the protein topology, prepare the ligand topology, define the unit cell and adding solvent, adding ions, energy minimization. But don't panic. Actually, each and every protocol is explained in detail. If you install Romax perfectly, then you can work step by step according to the tutorial guided from the home page. And if you see this MD simulation protocol, okay, to work on each and every steps, we have separate commands. This is what I mentioned as tools. Okay, we have exe files like GMX setup is to produce the topology using Chromax for a given section, and GMX solvate to solvate a system. Okay, energy minimization you have EM, and MD simulation generally SIM. Position rest to calculate position restraints. Likewise, has plenty of commands. Each and every command is used for a specific application. Okay, you can get all these details also in the website itself. Okay, now I told you what is Chromax, what for it is used, how the MD simulation is done, what are the general parameters we keep in MD simulation in software. So all these things I mentioned. Now I'm going to explain something about the outputs generated from the MD simulation. How can we see the outputs, sir? So if you see the docking, okay, in docking you're showing 2D interaction or 3D interaction. You're telling even the hydrogen bonds length, etc. But how about here? You're not going to get all these details in MD simulation, but you get details like root mean square deviation. This is one such a kind of a graph. Okay, here you can able to find what is first RMSD. One should understand it is the measure of the average distance between the atoms. Okay, that is if you have one atom, okay, and if you have another atom, the distance between, okay, so if you have like this, okay, distance between one atom, this is the intraatomic distance, isn't it? So if you have uh, uh, so even during the modeling of a protein, okay, so if you modeled a protein and if this is your X-ray structure, and if you have modeled a protein like this, okay, and if you find the sorry, the control is, I can't able to make it out. Okay, the distance between the center of radius to the another radius. If you see here, if you have 100 amino acids, but I have taken only first 2 amino acids, you can find some distance here. Excuse me. You can also find a distance from here to here. Of course, the distance between atom 1 to 2. Okay, so a kind of this kind of a distance will give you about how effectively you have modeled a protein structure. If the deviation is more, then whatever you model is not perfect, is not precise. If the deviation is very less, you can tell whatever structure you have modeled is good. So the root mean square deviation in terms of modeling, you can tell that uh, the least value of RMSD gives the better modeled protein. And even in simulation, here the RMSD, okay, here you're going to check a docking of ligand with a receptor. Okay, here this is an example for a protein modeled using Swiss modeler. But even if you try to dock, okay, a ligand with a receptor, even one atom of a ligand is going to dock with one atom of a receptor, isn't it? If so, okay, here also you can able to calculate the root mean square deviation. So in this, okay, calculation, this is the formula generally use it, okay, to determine the intraatomic distances. And if you want to do this using the software, obviously you can use this for command. So GMX spacebar RMS. Actually, this step you do only after doing this up to after completing the eighth step. During the analysis, you go for RMSD, RMSF, and other kind of simulations. Okay, so this is the final analysis, like how I go for docking analysis. This is a simulation analysis. Uh, so to work on RMSD, obviously you should use this kind of a command and attribute, and this is the file, intermediate file, XTC file, and you use a knife and again an attribute. This is again one kind of an intermediate file, an attribute, and .xvg. So this is the final output file. So RMSD output .xvg looks like this. You can't able to open this it in Microsoft Word or Paint something, etc. So the only visualizer which generally you can use it is XVG Grace, XM Grace. Okay, we use a tool called XM Grace. Okay, for visualizing the RMSD files. Here, if you see this in this example, okay, here I not only docked a ligand with a receptor, so the black one shows yeah, only the receptor alone. Okay, RMSD nanometrics in y-axis, time in picoseconds in x-axis. So in this graph, the ligand binding with the receptor is shown in red color. So this is with ligand. So this is without ligand. So actually, you have to get a result that with if you get a ligand binding with the receptor, I mean the value what you get for the ligand receptor, if it is low when compared to without ligand, your result is good. But if this black line is lying below the red, I can't tell the your ligand is binding well with the receptor. I can't tell. Okay, if the black is here, I can tell the ligand is not binding well with the receptor. I can click X. And similarly here also, I tried with another receptor. Here also get the red line below the black line. But you see the black line is somewhat stable, more stable after a certain time. But for the red line is stable for a certain time, but you found unstable for a certain time. And again, you find some stable for a certain time. And again, you find a somewhat changes in RMS. So you don't find a stable binding, but you can able to mention at what time it is stable, up to what time it is stable. Okay, so this is something about RMSD result, root mean square deviation. That is how effectively a ligand is binding with a particular atom of a receptor. Next, RMSF. What's the time now? So A2. So I think I have few slides. I can able to complete it. Just give me spare me 2 to 3 minutes. I try to complete it. RMSF, root mean square fluctuation. So root mean square fluctuations tells you about carbon alpha fluctuations, C alpha fluctuations. Okay. So if you see the C alpha fluctuations, RMSF in y-axis and residues number is in x-axis. So if you find a large peak here, so at this particular residues, okay, the amino acids of the protein is not stable. Okay. If you find more peak, okay, this amino acid region alone is not stable. So this is how we can able to show the result for RMSF. So this is based on purely on the carbon alpha fluctuations. And for working on RMSF, of course, in the ninth step, so after RMSF, you can try to run the RMSF using this command. And you get like rmsf.xvg. This you can open in XM Grace tool to get a kind of a result like this. This is just a ligand with this is just a receptor alone. Okay. Here, if you see here, I have both the ligand bound and without ligand bound. So if you see with ligand, okay, the red color, I can find this is unstable at this particular residues. Okay, so this alone I report and tell the ligand is not binding well. But see, without ligand also the black color you can find a large peaks. So our ligand is binding effectively in this residues. So only in this residue alone, whatever I shown in the red, this alone, you don't find our ligand is binding effectively. So like you can show infer the results of the from the MD simulation. And the third result is about the radius of gyration. So radius of gyration it tells about the axis of rotation. That is, even the atoms have a kind of axial rotation. Okay, so where you excuse me, where you come across momentum. Okay, so you check for how. Yeah, so here if you see the radius of gyration, it defines the radial distance to a point, moment of inertia, the same as the body's actual distribution of mass. If the total mass of the body were not concentrated. Like for example, if you see mm, the proline is not going to have a much kind of a moment of inertia, but whereas if you see some amino acids like lysine is going to have a good kind of a rotations. Even this kind of will contribute something related to that. And if your ligand, especially if I speak about the ligand receptor interactions, if your ligand is more having a rotable bonds and it's having a kind of a moment of inertia, obviously you can find more radius of gyration. So according to this, how can I infer the result? From the result, I can tell, okay, this is not stable over a period of time up to this. But after some 30 nanoseconds from here, you can find the stable. Okay, up to this. Up to this, I can tell it is stable. Again, you find unstable. Again, you found this. Okay, so this is how we will be mentioning the kind of output. Okay, so this generally measures the compactness of the structure, whether your protein structure is compact or not. Okay, so how effectively your structure is compact, this is determined from this radius of gyration. Now, let me take you to the binding free energy. In binding free energy, you have different forms of energy: MMPBSA, MMGBSA, and LI, linear integration, linear interaction energy, linear interaction energy. GBSA is molecular mechanics generalized bond surface area. What is MMPBSA? Molecular mechanics Poisson Boltzmann surface area. Okay, now let me explain about this. There are actually three different outputs. One is one trajectory. That is, if you're binding a ligand, okay, if you're binding a ligand with a receptor, okay, so if you want to see this energy here in one trajectory, one should have a knowledge on the Gibbs free energy of the ligand, Gibbs free energy of the receptor, and the Gibbs free energy of the both the ligand receptor complex. Okay, so these three are taken considered in three trajectories. So actually, whatever formula here I've shown is for these three trajectories. If you consider all these three interaction energies, then you can go for three trajectory. But if you're considering on one trajectory, you focus only on this alone. This energy alone you calculate in one trajectory. But in three trajectories, you consider each and every thing whatever shown here. And if you see this kind of linear interaction energy, you come across two trajectories. One is the ligand, the other is ligand and receptor complex. These two alone we take in two trajectories. For this, you can use this formula. Got it? In a PBSA, you have one trajectory. GBSA have three trajectories, and LI is going to use two trajectories. So two trajectories, just ligand and ligand receptor. One trajectory, only the ligand receptor alone. And three trajectories, you use all the three energies for calculation of total binding Gift energy. Got it. Molecular simulation, we can also check the secondary structures from that and PBSA versus time. All these also the other outputs of Chromax. Yeah, I think I've completed my session on AMD simulation using Chromax. Okay, if you want to work on Chromax, I told you no. So see, even simply go to the chromax.org. Okay, and you can find plenty of information on the tutorial on how to download the software. Myself, I downloaded and just worked okay without any help. Okay, just tried manually. Of course, it's working successfully. So see, each and every sub steps, everything was mentioned there. Okay. Any doubts you can ask me now. Do you have any doubts?
Sir,
Mm.
can you mention that 15 tools that are used along with the Gromex? Can you give us the
Uh,
name?
yeah. Actually, all these things, okay, it's available, so I can show you. I better paste this, okay. Whatever I mentioned, okay, the programs on the commands, okay, you can find from this URL. You can use this URL, okay. So check from this. Any other doubts you have? Okay, participants.
Thank you.
Thank you for the interaction from the beginning. Um, so tomorrow